Hello everybody, and welcome to another lecture of algebra for intermediate algebra. And today we're going to be looking at ratios some more. When I say ratios some more, we've already talked about rational expressions and rational equations. And the root of the word rational is ratio. So in 7.6 we're going to be looking at ratios and proportions and some problem solving. Now today's lecture is going to be in two parts because we're going to first of all address ratios, proportions, and some problem solving, and then we will finish up with part 2 of the lecture, or part B of the lecture, when we deal with more advanced problem solving. But first of all, let's define what ratio means. All right, the word ratio has its basis in the word rate, and we all know how to determine rates. Okay, we can determine the rate of the price per item by dividing the total price that we pay for a certain number of items. We can figure out our miles per gallon by dividing the total number of miles that we traveled over the number of gallons that we filled up our tank with. So we deal with rates all over the place. But the ratio of A to B, when we're talking A to B, we're talking about the ratio of two values. It can be written in this way, A colon B, or A to B in words, or as the fraction A over B. Ratio is quite simply the quotient of two numbers. All right, when we talk about ratios, units are going to be extremely important. All right, the reason that I mean units are going to be extremely important is whenever you figure out your miles per gallon, all right, you're not trying to calculate price per item. You're trying to figure out miles per gallon. And whenever you figure out how fast you've traveled to get from one point to another, you're figuring out miles per hour. So we have to keep in mind that units are extremely important. For instance, if you buy $52 of gasoline, now that doesn't seem like much anymore in today's economy, but if you were to buy $52 of gasoline and you were able to purchase 13 gallons, to find the price per gallon means that we would divide 52 over 13. But what's important is that we keep in mind our units of dollars over our units of gallons. When we do that, we then calculate it and do our division. We end up with $4 per gallon. Per is simply a word meaning ratio. It really does. It just simply means ratio. So every time we deal with a rate, we're going to be using the word per when we're dealing with a rate. Now, not every ratio has units associated with it, but this right here is called a rate. And the word per is operative for rate. All right, so now let's recall fraction simplification. Hopefully you recall fraction simplification. When we looked at simplifying fractions, we had like 12/14 and we simplified it to 6/7. Remember, when we took 12/14, we found out that both the numerator and the denominator divided by 2 by the fundamental principle of fractions, and we ended up with 6/7. Now what we have here is a proportion because we have 12 over 14 equals 6 over 7. What that means is the exact same thing is done to the numerator as it is to the denominator. We can create any kind of proportion as long as we do the same operation to the numerator as we do to the denominator. So a proportion is defined as two equal ratios. Here's an aside note. Is 5/8 equal 10/24 a proportion? Well, if we look, when we multiply 5 over 8, if I want to get to 10, then I would multiply the numerator by 2, right? And if I multiplied the denominator by 2 as well, we would end up with 10/16, not 10/24. So in answer to this question, is it a proportion? No, it is not a proportion. The reason it's not a proportion is the same operation of multiplication or division is not done to both the numerator and the denominator. So, let's also recall how we cleared fractions to solve rational equations. Ladies and gentlemen, we have this A over B equals C over D. Now, if we clear fractions the way that we learned in the previous sections, then we would look at the LCM as BD. What do? We multiply both sides of this by BD. And on the left, the B's cancel, so we end up with AD. And on the right, the D's cancel, so we end up with BC. Now notice, though, that since we have a single ratio in each side, we can use a little bit of something different. What is that something different that we can use? We can use what's called cross products. Now let's explore cross products. We have this ratio, or this proportion of A over B equals C over D. A over B equals C over D. By using cross products, we end up with AD equals, and then we cross the B and the C, equals BC. Now, isn't that the exact same thing we had right over here? It is, isn't it? So by clearing the fractions with a proportion, we end up with the same thing we get when we use a cross product. So, we can use cross products to solve proportions. Now I'm going to give you a warning. Warning. To use cross products, we must have a proportion. In other words, one ratio equaling another. Let's look at this example here, the example that I started right down here. We're going to move on to the next page because we need a little bit of room for this. Do we have a single ratio on the left? Yes, we do. We have a single ratio right over here because there's just one single fraction bar. We have a single ratio over here as well. So what are we going to do? We're going to use cross products. 3 times x plus 1 equals 5 times x plus 2. We've successfully cross-multiplied the two of these. Now, after we've done that, let's take a look at what we have here. What we have here is an equation that doesn't have any fractions in it. Sounds kind of like that first step when we talked about solving rational equations and then solving rational equations for designated variables. That the first step we always do is clear fractions. Well, right here, ladies and gentlemen, we have no fractions. And then we clear parentheses, if you'll recall, from the steps. So let's take a look at this here. So cross products is just another way that we clear fractions. It's really the same thing that we've been doing. It's just a shortcut. So once we do that, then of course we isolate our variable term, as we've done so many times in the past in solving so many of these, and we get 2x equals negative 7, so x equals negative 7 halves. Now, it's very easy to check this. We have negative 7 halves plus 1 over negative 7 halves plus 2. Negative 7 halves plus 1 is the same as negative 7 halves plus 2 halves, and negative 7 halves plus 4 halves in our denominator. So we end up with negative 5 halves over Yes. All right. Negative 5 halves over negative 3 halves. The 2's cancel because whenever we divide fractions, if you'll remember, we multiply by the reciprocal. The 2's cancel, the negatives cancel, and we end up with 5/3, which is exactly what we have right here. So this works, therefore, there is our answer. So we can use this process to solve so many types of proportions, yes. Oops. Yes, that's where we needed to go next. I apologize. Let's look at a problem-solving application. Now, this comes from your text. If a 170-pound person weighs approximately 65 pounds on Mars, how much does a 9,000-pound satellite weigh? All right. To set a proportion up, we have to declare what we are comparing. Okay, what are we comparing? We're comparing two items. What are we comparing? We're comparing the weight on Mars to the weight on Earth. So we've got weight on Earth compared to the weight on Mars. So a 170-pound person would weigh 65 pounds on Mars. Pounds over pounds, the pounds cancel. All right, good. But this is a proportion, ladies and gentlemen. It's a proportion. How much does a 9,000-pound satellite weigh? So 9,000 pounds. We've got this 9,000-pound satellite, and we're fixing to launch it to Mars. Right now it weighs 9,000 pounds and we're on Earth. So where would the 9,000 go in the numerator or the denominator of the other side? Well, we have to maintain consistency with our ratio all the way across here. So the 9,000 would go in the numerator and our unknown would go down here. Now the question is, do we have a ratio? Yes, we certainly do have a ratio here. So we're going to cross multiply, or not a ratio, yes, we have a ratio here. We have a ratio here. A ratio equals a ratio is a proportion. So we can use cross products. So what do we have here now? 170x equals 9,000 times 65, which is going to give us 585,000. Now we would divide. So 585,000 divided by 170 gives us 3,441.176. And typically we would round these to whatever the instructions tell us to, and I apologize that I didn't give you the instructions on how to round that, but we would go ahead and round that to 3,441.2 pounds. Now hopefully that makes sense to you, that we always want to make sure that we compare the same. The ratio needs to be the same through the entire proportion. So right here we had Earth's weight on top, Mars weight's on bottom. Now let's look at how we can use this. We've already done this with the gasoline example a few moments ago. But what we're going to do is we're going to compare prices charged for various sizes of picante sauce. Let's find the best buy. All right, so the first thing we're going to do is we want to find the price per ounce of each and compare. Price per ounce. So we have $0.99 over 10. Now once we divide that by 10, ladies and gentlemen, we're going to end up with $0.099. Now when we start getting to that small of a number, we should probably convert this. So what is it going to be? 9.9 cents per ounce. How did I convert that from dollars to cents? Well, hopefully you'll recall from your arithmetic days that when you convert from dollars to cents, you move the decimal 2 places. All right, let's look at this other one. 1.69 over 16. Now this one may not be quite so easy. And notice we keep track of our units here. So we're going to take the calculator and divide this. 1.69 divided by 16 gives us 0.105625. Well, we're going to have to change the, oops, this was dollars per ounce. Sorry about that. And then it's which is going to give us 0.09, 9.9 cents per ounce. All right, now this is dollars per ounce. Moving the decimal over, it's 10.6 approximately cents per ounce. All right, let's look at the next one, which is $3.29 over 30. All right, now that's dollars, and this is ounces. So 3.29 divided by 30, 3.29 divided by 30 gives us 0.10967 dollars per ounce, which moving a decimal over is 10.97 cents per ounce. Of these three, which is the cheapest or the most affordable of all the picante sauces? 9.9 cents per ounce, 10.6 cents per ounce, or 10.97 cents per ounce? Well, it looks to me like this one is the best buy. So the 10-ounce purchase is the best buy. And that's how we figure out rates and make comparisons. Now, unfortunately, when you go to your typical Walmart or whatever, right there on the little tag on the shelf, it already tells you the price per ounce. However, we may not necessarily want to always trust what that says there. So it's probably not a bad idea for you to double check the arithmetic. Okay? Let's look at another example here. Let's deal with proportions as they relate to similar triangles. What exactly do we mean by similar triangles? Well, similar triangles. The definition of similar triangles is right here. Similar triangles. the measures of corresponding angles are equal to each other. So this angle right here is equal to this angle. This angle right here is equal to this angle. And this angle right here is equal to this angle. The measures of the angles. So the degree measurement's going to be the same for the corresponding angles. As the result, the corresponding sides are proportional. What do we mean by proportional? Well, we can form a proportion from the small angle to the large triangle. So we form a proportion because the sides are proportional. The sides are not equal. The angles are equal. That's what makes the sides proportional. So the side measuring 6 here corresponds to the side measuring x. Let's take a look at that. What do I mean by that? This side 6 corresponds to this side x. This side 5 corresponds to this side 10. So we can use that information and what we know about ratios and proportions to solve similar triangles. So what we're going to do is we're going to use that information and compare the ratios of 6 to x over 5 to 10. Now we have single ratios. We can quite simply cross multiply. And then, of course, divide. It gives us 12. So if our measurements here are in inches, then our side here is 12 inches. That makes for really, really interesting information because similar triangles are used quite frequently. Similar triangles, there was a question about similar triangles that showed up in the GED tests and the ACT tests relating to how to determine the height of a particular tree. So what I want to do is I want to insert a page to do an example as to what I'm talking about here. Let me make sure that worked out okay. All right. The shadow length, the shadow length of a 4-foot pole is 9 feet long. The shadow of a tree is 27 feet long. How tall is the tree? Well, here's our situation, and always if you ever have a question about a word problem, it's not a bad idea to draw yourself a picture. So we've got us a tree here. We've got us a pole here. Now we know the length of the shadow of the tree is 27 feet. We know the pole is 4 feet tall. And we know the shadow of the pole is 9 feet. Now, if we connected this part, it doesn't have to be, perfect, but if we connected this and this, we would have 2 triangles. These triangles are similar triangles, so all we do is we set up a ratio. We don't know the height of the tree, but it corresponds, the height of the tree, which is x, corresponds to the height of the pole, which is 4. The shadow of 27 corresponds to the 9. And now to solve this, we go 9x equals 27 times 4. So 9x is going to give us what 27 times 4 is, and 27 times 4 is going to give us 108. So how tall is this tree? It's just coincidence that we ended up with the same value that we ended up with in the other problem, but the tree is 12 feet tall. You're going to have a number of those problems, and maybe a couple of those problems in your homework to work out. So it's very important that we understand how to work these similar triangles. Now let's look at simple translations. Simple translations. When we look at simple translations, we have to seriously consider carefully the wording of a problem. When we've got this word right here, quotient, that means we've got us a ratio. Well, when we look at all this, this is the quotient of a number and 9 times its reciprocal. The quotient of what? 2 things. A number and 9 times its reciprocal. That looks like a conjunction embedded within a prepositional phrase. So the quotient of a number and 9 times its reciprocal is 1. Okay, everybody? So what exactly do we have here? We have n over 9 over n equals 1. Well, if we cross multiply, now how can we cross multiply? Because 1 is a ratio. So when we cross multiply, we have n equals 9 over n. So we've cross multiplied because 1 is the same as 1 over 1. The issue is now we've got also to cross multiply again, so we get n squared equals 9. Now, how do we solve that? Well, if you remember in our previous section, we talked about once we get to clearing the fractions, then we determine whether it's linear or not. This is not linear. It's quadratic, so that means we have to set it up. We have to set it up equal to 0 and then factor. The left-hand side is a difference of 2 squares. Since it's a difference of 2 squares, then we solve it by setting each one of them equal to 0. So x is going to equal 3, or x is going to equal negative 3. Very easy to check that by plugging it in over here. 9 times 1 over 3 is 3. 3 over 3 is 1. Negative 3 over 3 is 1. So both of these answers work just fine. Okay? Now, this concludes the first part of the lecture, and we will be finishing up this lecture in the next video. Please, if you have any questions while you're working through these problems, don't hesitate to let me know. Give me an email, send me a question from the Ask Your Instructor a Question feature of My Math Lab. But it's important that we get going and move forward with your homework, okay? That's it. Thanks.